flow chart here, and that the purpose of this flow chart is to look at the chain of events, especially how negative and positive feedback play into this. All right. So let's begin with our threshold stimulus. Right? This is one that gets to negative 55. Okay. This is going to depolarize the membrane by way of opening up our voltage-gated sodium channels. This results in an increase in the membrane's permeability to sodium, which means that sodium can rush into the neuron. All right, so sodium flows into the cell according to its UCDF. That results in a net positive charge in the cell, which is a depolarization event. And that's also an example of positive feedback because we're opening up nearby sodium channels that is further potentiating the movement away from our set point. Now, when we open up these sodium channels, there is also the delayed 1 millisecond effect. This is specific to the inactivation gates on the sodium channels. So 1 millisecond of the sodium channels being opened, and then they will automatically close. The inactivation gates will close. Okay. Now the membrane permeability to sodium should decrease. There should be a down arrow here. I'm going to go ahead and draw it in. Please draw it in on your slides if it's missing. So the membrane permeability to sodium will now begin to drop or decrease because we've closed those inactivation gates. So the channel is closed and incapable of opening. And now we have decreased inflow of sodium to the cell. And we have a net positive charge in the cell. So this is basically encouraging or initiating repolarization, right? So as we have less sodium entering the cell, we're beginning that change, which is repolarization. But we also have to think about potassium's movement at this time. So we also have another 1 millisecond delay. Remember, when we depolarize the membrane, 2 millisecond timers are triggered. One is for the inactivation gates on sodium, and one is for the potassium gate. So there's only one channel or one gate on potassium channels. And that is also going to be triggered as soon as the membrane depolarizes. So these two events are synchronized. That's why we have this timing event. This is to allow for the perfect synchronization of the closure of sodium channels and the opening of potassium channels by synchronizing them using this 1 millisecond time delay. All right. So now we have opening of potassium channels after that timer goes off and potassium channels open, which is going to increase the membrane permeability to potassium. So this should have an up arrow. This one should have a down. Okay. So the membrane permeability for potassium begins to increase as potassium leaves the cell. This is going to further encourage repolarization, right? And that is going to help return the membrane potential back to rest, okay? Now, potassium's movement, or when we get back down to our resting membrane potential, that is an example of a negative feedback. Okay, now I'm going to share this drawing with you guys. I encourage you to practice this as homework. All right. So I encourage you to practice this as homework, practice drawing this out on your own. I do want to explain here, just to kind of go over this a bit, but I encourage you to draw this out on your own as a way to really make sure you understand how the membrane potential is changing, what ions are moving, and what the state of the permeability of these channels are, what the state of the channels look like to result in the membrane potential change. I do want to explain here the iPSP and EPSP. We haven't gotten to this yet. We will when we look at the synapse, but these are basically synonymous with hyperpolarization and depolarization. So iPSPs are negative membrane potential changes, and iPSP stands for inhibitory postsynaptic potential. Let me actually write that out. All right, so an iPSP is an inhibitory postsynaptic potential, and EPSP is going to be an excitatory postsynaptic potential. All right. So basically, these are types of graded potentials that we will speak about. So if it is a negative chain, it will be an iPSP. If it is a positive chain, it will be an EPSP. And these are the types of graded potentials that can undergo summation, either spatial summation or temporal summation, and could potentially get us to threshold. And then from there, we have depolarization, which is the increase in the membrane potential from negative 55 to positive 30. Here we have activation gates open, inactivation gates open, and we have potassium channels closed. For the repolarization phase, we have sodium gates closing, right? The inactivation gates specifically are closing because of that timer. Potassium channels open, and then we have the downward change in the membrane potential. And then phase 4 here is the hyperpolarization change, which is where we have potassium channels are closing. So they're not totally closed. This is why we don't stop at negative 70. We go to about negative 85, and then with the help of the sodium potassium pumps, we return this to rest. So again, take some time over the next few days or so and try to practice drawing this out as a way to test that you can integrate all of these various concepts. And then another set of study tools here that could be helpful are these summary tables. So ways to compare the state of the voltage-gated sodium channels, the movement of sodium, the voltage-gated potassium channels, and the movement of potassium when the membrane is at its different states. So when it's at rest, when it is depolarized, when it is repolarizing, and during hyperpolarization. So I encourage you to block this table out. So maybe try to delete or block all of the central columns and try to fill this in from your memory, from your understanding, sorry, not your memory. So don't just memorize it, but really understand why is the resting membrane potential negative 70, right? We talked about how we established that value. So make sure that you're definitely understanding how the different areas of this column, how those things are so, and not just memorizing what those values are. And then another good study tool here, this one is comparing the graded potential to the action potential, especially as it applies to the all or none principle. So the fact that the action potential is always the exact same strength, okay, it's going to be graded for graded potentials. It can be weak, it can be medium, it can be small, it can be strong. For graded potentials, that's what graded means. But for the action potential, there's no way of grading it other than improving or increasing or decreasing the frequency. So that's one major difference. Another one would be the location. So on the dendrites and the soma of the neuron is where we have graded potentials. Along the axon is where we have action potentials, and so on and so forth. So this can be an excellent study tool to just summarize and differentiate these two potentials. So let's look at the next set of, actually, let's skip over these checkpoint questions. Let's begin with these on Wednesday, just because I want to have enough time to discuss and we don't have much time left. So I'm going to skip over these and we'll begin our discussion on Monday with these. As usual, I encourage you to write your responses down. That's the best way to make sure that you're understanding it and that you are able to reflect back when you're preparing for exams. Let's go on to lecture objective number 3. So describe the refractory periods, including what causes the absolute and relative refractory periods, and then we're going to explain their physiological significance. So why are they important? Now, the refractory periods are periods in time immediately following the action potential where we cannot fire another action potential, or it's extremely difficult to fire another action potential. So the action potential can only increase in frequency to a certain point. So while this is the way that we can increase a signal or a stimulus, there's a certain point where we can no longer increase the speed of the action potential because of the refractory periods where the neuron cannot be excited immediately following one action potential. Now, the absolute refractory period is going to be during the action potential. This is when the sodium channels are inactive. This is when the inactivation gates close. And so this is a brief period around the action potential. So while it is occurring, but also immediately following the repolarization phase. And this is where it's impossible to stimulate a subsequent action potential. All right, it's impossible. Why? Because the sodium channels are inactivated. Their activation gates are closed, but their activation gates are open, but their inactivation gates are closed. And so even if we had a really strong stimulus come along, that neuron needs to get back to rest before we can trigger another action potential. The relative refractory period, however, is when potassium channels are still open. So we could fire another action potential, right? Because now the inactivation gates on sodium have been reset, so they are open. So the channels are closed, but capable of being open. However, because potassium channels are still closing, the membrane potential here is very negative. It's below -70 and about -80, 85 or so. So it's going to be harder to depolarize the cell from -85 to -55 than it would be to depolarize from -70 to -55. So in the relative refractory period, it takes a very strong stimulus simply because the membrane potential has overshoot and it's way more negative than -70. So we need a stronger stimulus to take us from -85 to -55. And so we could fire another action potential, but it's going to require a strong enough stimulus. All right. So in the absolute refractory period, because of the inactivation gates on sodium channels, it is impossible to fire another action potential. And this is going to be immediately during the action potential, but right after repolarization. So in that initial 1 millisecond time period. The relative refractory period is going to be a few milliseconds after the repolarization. And this is that time of hyperpolarization where the membrane potential is still very negative. So it's going to take a stronger stimulus, but the sodium channels are capable of opening. So we could fire another action potential, but we just need a strong enough stimulus. So just to reiterate this again, the absolute refractory period spans all of depolarization and most of repolarization as well. This is where sodium gates are inactivated. Again, it's roughly that first millisecond or so. The relative refractory period spans the last part of repolarization, so the very end of repolarization, and all through hyperpolarization. And this is where a second action potential can be generated, but with a stronger stimulus. Okay. And another reason to explain the relative refractory period is that some sodium gates are closed and some are inactivated. So there's also a transition happening with the sodium gates as well. They're not all, they have not all been returned to their resting state. So some of them are still inactivated. Some of those inactivation gates are still slowly opening up as we try to get back to rest. And so there's a transition happening, which is another reason that it is harder to fire a subsequent action potential. So that would be the period during hyperpolarization. Okay. Let's go to objective number 4. So we're going to describe the propagation of action potentials from the axon hillock to the axon terminal, and then we're going to compare what happens in myelinated versus unmyelinated axons. Now, we've been speaking about the action potential in a very sort of abstract way. We've been talking about how the ions are moving and the membrane potential is changing. And we want to kind of zoom out at this point and really place this into its perspective along the physical structure of the neuron. So when the action potential begins on a neuron, it's going to start really at the axon hillock, so about the neck region or so, and then it's going to travel in this direction. Now, the fact that it's only going to move in one direction is part of the features of the neuron itself, right? The state of the channels along the length of the axon. So when voltage-gated sodium channels open up, they open up in a wave that move down the length of the axon. So when the action potential gets to one site in the neuron, it's going to open up the sodium channels here. It's going to depolarize this initial segment, and that is being reflected by the positive ions here as sodium rushes in. Now, what's going to happen is the action potential is going to jump to the next segment along the neuron. However, the segment that was previously depolarized is now going to be in its repolarization phase, and it's also going to be in its refractory period. So it would be impossible to depolarize the previous segment. And this is why the action potential moves in one direction, because of that refractory period. So we can't depolarize the segment that we've just depolarized, but we can't fire another action potential here right away. And so the action potential has no choice but to move in one direction only. In the lower panel here, we can see that the first segment is now completely at rest, so it's been returned to rest. The middle segment is now in its repolarization or refractory segment. And then the third segment here is now being depolarized. So this portion of the neuron could receive another action potential, but the portion immediately preceding the depolarized region cannot. So the action potential cannot spread in the reverse direction. Okay. All right. Now, because of that, because of the fact that the action potential is moving from one segment to the other, to the other, to the other, that can become very, very slow in neurons, right? And so a way to speed up the conduction of a neuron is going to be by myelinating it. So let's look at what happens in an unmyelinated neuron. So here's our neuron at rest. Here is when we depolarize site A. The action potential then jumps from site A to site B. If you look at the third panel here, site B is now depolarized. Site A is now in its refractory state, so it cannot be depolarized again, at least not immediately. And then site C is going to receive the depolarization next. So this is moving the action potential from one segment to the other. And because there is no myelin, this is an unmyelinated axon, the conduction time here is going to be much slower, right? Because the action potential has to physically move from one site to the next, down the entire length of the axon. If we contrast that to what happens in a myelinated neuron, skip over this. A myelinated neuron provides insulation. So the insulation actually acts like a cable. It speeds up the conduction property of the neuron. So instead of the action potential moving from one spot to the other, to the other, to the other, it just leaps over in between the gaps of this myelin. So this is the myelin sheath, right, which are basically wrappings of fat around the neuron. These are fatty layers or coating around the neuron. And they have these gaps or these openings that we call the nodes of Ranvier. And so the nodes of Ranvier allow the action potential to leap through the axon, through the length of the axon, by jumping over segments that are myelinated. All right, so this is called saltatory conduction. Saltatory conduction means that we're not going local from one to the other. We're kind of jumping over these myelinated segments. And as we could imagine, this rapidly speeds up the conduction of the action potential down the length of the neuron.